Okay, then, good morning, everyone. Welcome again. Okay, so we're going to continue looking at sequences today. We started just with some very initial definitions there yesterday. So remember, this is the third lecture in the week. This one will alternate between myself and Saeed week to week. And then either later today or tomorrow, I believe the tutorials will take place. Saeed, Gotcha, and Ryan. I'll be giving you out at the end of today's lecture a further set of exercises, tutorial exercises, which will be a good source of exercises for using your tutorial on my app, on the sequences app. In Saeed's part, the tutorial exercises are spread throughout these. Also, just kind of experimentally myself, I'm experimenting with recording my lectures just off my laptop that's sitting there on the table, records the screen and the audio in the room. So if you look on the Moodle unit, you can now see this bit here near the top, which is a YouTube playlist. It's only got one video in it at the moment because I only just gave yesterday's lecture. But as we go through the course, the playlist of videos here will expand, and this will have all the lecture recordings of all of my lectures. Saeed isn't doing it, it's just me. So you can watch the lectures back there. Now, I didn't, in that particular lecture yesterday, I didn't produce any handwritten notes, but I do like to do handwritten examples and extra explanations during the lectures. When I do any of those, well, as well as taking notes yourself, but I will, whatever pages I produce here, I usually scan those, and you'll find a little link to it just in the description of the video there. Okay, so hopefully that's a good visual resource for you going forward. When you want to revise parts of the course. And so there we go. Okay. So, yesterday, we introduced the notion of convergence as a useful concept in science generally and in mathematics particularly. And then we started to get a bit more detailed and study, well, we're going to be studying the concept of convergence in mathematical sequences. Later on, we'll be studying it in series, which are where you add up all the elements of the sequence, and then later still we'll be looking at functions and calculus, and convergence is a key ingredient into the notion of the derivative and the integral and so on. Okay. So yesterday we just met this first definition of a mathematical sequence. This is going to be a sequence of numbers for us, usually. Normally the ones of interest for us will be infinite sequences that go on and on and on. And then we can talk perhaps about what the limiting behavior of these infinite sequences. So a sequence is very simply just a list of elements. Okay, a first element, a second element, a third element, and so on and so on. So that's normally denoted by letter X with the index being in the subscript position. So x1, x2, x3, x4, first four elements of the sequence. We can refer to the sequence as a whole, well, either like writing it down here with a suggestive continuation there, or using this curly bracket notation. So curly brackets xn will be referring to the whole sequence. And if needed, if it's required, if it's useful, we can put down here the starting and ending values of the index n. So this tells us that the sequence begins at position position n equals 1, and it continues without any end. That's because of the infinity in the superscript. If there was some number here in the superscript, like 100 or something, then that would just be a sequence of 100 elements, a finite sequence. But very often we'll drop that information and we'll just refer to curly brackets xn as referring to the whole sequence. Okay, now I went through these slides yesterday. We looked at some examples of the sequence of integers, Fibonacci sequence of odd integers. And sometimes these had a nice formula for the nth element of the sequence in terms of the value of the index. Zn equals n for the sequence of integers. An equals 2n minus 1 for the sequence of odd integers. I'm just going rapidly through this. We did this yesterday. Or we can add things like this, which is a recurrence relation. This is defining the Fibonacci sequence, where after you just declared what the first two elements are, F1 and F2, subsequent elements are defined in terms of previous elements. So Fn in particular for the Fibonacci sequence, Fn is the sum of Fn minus 1 and Fn minus 2. The two preceding elements, the two elements that came before Fn. And then more or less where we finished yesterday was just some very interesting, important sequences aren't possible to define like that. There's no simple formula that's going to tell you what the nth prime number is. We discovered the list of prime numbers up to a certain limit using computer search, but beyond that, there is no way we can just simply jump to a certain position in the ordered list of prime numbers. They can't be described in such a simple way. But we do know that they're an infinite sequence. Prove quite without too much difficulty that the sequence of primes is infinite. We'll see that in the second year number theory course. Okay, so this is coming on to some new concepts now that we didn't go through yesterday. And so just a few more definitions and examples. Some of you may be familiar with these from your previous math study. So we have the notion of, so these are two important families of sequences. We've got arithmetic sequences and geometric sequences. These are sequences that proceed in a very well-behaved way, and they're very easy to analyze because of that. So an arithmetic sequence is one that proceeds by just a fixed step size. The sequence is coming along, and each next element of the sequence is just a fixed increment, a fixed increase or decrease, say, but a fixed difference from the previous element. And that difference doesn't ever change. That step size doesn't ever change from one element of the sequence to the next. So in very general terms, there's some first element of the sequence A, and then the next element is just A, that previous element A plus some fixed step size, which we'll call D for difference if you like. Then the third one, well, according to this rule, you're just adding on that same difference. So the third element is going to be A plus 2 times D. The fourth element will be A plus 3D. And it just continues in that same pattern. So the formula for the nth term of an arithmetic sequence like this is apparent from that. So the nth element, an, can be written as the first element, a, plus n minus 1 factors of d. So you take n minus 1 steps to get the first element to the nth element. But that's an arithmetic sequence, one that proceeds by adding a fixed amount. A geometric sequence is exactly the same idea. When you're not adding a fixed amount now, you're multiplying by a fixed amount. So it's not a constant difference you're adding on now, it's something like a constant scaling factor. So when we say scaling factor, we mean that we multiply the quantity by some factor which scales it up or down. Okay. So in a geometric sequence, you have a first element A, the second element A multiplied by this scaling factor R. And the third element will be the second element, AR, multiplied by that same scaling factor R. So the third element becomes AR squared, fourth element AR cubed, etc. Or R might be referred to as a constant ratio, perhaps, the ratio between consecutive terms. And the formula for a geometric series is a similar kind of structure to the arithmetic one, but this time using the operation of multiplication. So we're not adding here, we're not multiplying by n. Instead, we're multiplying and where we have n in the exponent position. So the nth element, an of geometric series, is an is a times r, and the r is to the power n minus 1. Okay? But we may well have met these terms before. So some quick examples. I mean, if you did, yeah, so the sequence of positive integers themselves are an an arithmetic sequence, because an is equal to n, and trivially that's just 1 plus n. So the initial term a will be 1, and the constant difference d is 1. So that's not that particularly interesting. And the sequence of odd positive integers that we looked at already as an example of a sequence, that is also arithmetic. So it has a first element 1. And we just step into the odd integers, so the fixed step size and the fixed differences are 2. And so the arithmetic style formula for the odd integers would be an is 1 plus 2 times n minus 1. So these are in your notes, page 3. Next example, which is example 1.3, your notes on page 3. This is the sequence of powers of the half. If you look at 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, 64, 128, 156. And those are all the powers of 2, or the reciprocals of the powers of 2. And that's a geometric series, okay? Because each element in that sequence is half of the previous one. So to generate the next element in the sequence, you're always using this fixed scaling factor of half. Okay? So it's a geometric series. And to write down its geometric style formula is this here. So, well, remember before we had the geometric style formula was AR to the n minus 1. Well, in the case of this sequence, A, the first element is just simply 1. So we don't actually write it down. Imagine an extra factor of 1 out here, but that doesn't change it. But the constant ratio of r is a half, and that's to the power n minus 1. That's the rule for generating that sequence. But slightly more interesting, and this will be something you'll encounter. I mean, this is the most simple version of it, and you'll encounter this kind of thing if you're studying these stats and statistics units or the financial units in the second year. And I'm sure you've seen it already, something everybody should be aware of, really. They're mathematics students or not, but just the compound interest formula. So if you were to, so this is where you're placing, say, an amount in savings account. So if you were to put an amount of P pounds, P stands for principal, which is the initial investment, the initial loan, whatever. But if you were to place an initial amount of money P in a simple savings account that paid an annual interest rate of R%, and you weren't to pay any more into it, just to leave it there growing under compound interest. At the end of the year, the bank credits the account with R% interest of what the balance was at the start of the year, and then that process is repeated year on year. Well, then the future value, Vn, of that account will be given by this formula here, and we recognize that as being the formula for a geometric series. Okay? So some initial term, which is P, the initial investment, and then each subsequent element in the sequence is just previous elements multiplied by this scaling factor, which is 1 plus the interest rate over 1 plus the interest rate. That's the interest multiplier, which applies to the value each year to give you the value for the next year. Now, depending on when the compounding is done, if it's every month or every week or continuous compounding, then that formula changes a bit. And if there's regular investments put into the account, that complicates the formula. Or if it's describing a loan with repayments, that complicates it yet again. Okay? But the basic idea is this geometric effect of reoccurring compound interest. Now, the world would be extremely simple if all sequences were either arithmetic or geometric. They certainly aren't. These are extremely special cases of sequences that have a very specific behavior. And it's very easy to write down examples of sequences which are neither arithmetic nor geometric. Such as this one, the sequence of the reciprocals of the squares of all the exponentials. So the sequence defined by this formula, xn is 1 over n squared. Okay, that is not arithmetic or it's not geometric. Increments from one sequence element to the next are getting smaller and smaller and smaller, so certainly they're not constant. And if you were to look at the ratio between one term and the one before it, they are getting smaller and smaller and smaller and smaller. Okay, so there's no fixed difference or no fixed ratio. So that's just some definitions and examples. Any queries on that or clarification that I could provide? Okay. So that's in the notes on pages 2 and most of 3. So we're going to be looking at convergence, which some people like to say this is the long-term behavior of the sequence, the limiting behavior of the sequence, how the sequence is behaving as it continues. Long-term behavior. Just as a first, before looking at convergence itself, we'll just look at a much simpler aspect of the long-term behavior of the sequence, and that's the notion of an increasing or decreasing sequence. The technical term for such sequences is monotonic. So a monotonic sequence is one which either it is always increasing or it is always decreasing. Okay? Monotone. So, an increasing sequence, that means you'd have a collection of inequalities between neighboring elements like this. X1 is smaller than X2, X2 is smaller than X3. This might be weakly increasing. So some neighboring elements could be equal, but a following element is never smaller than the one that came before. It's always greater than or equal to the one. Similarly speaking, a decreasing one or a weakly decreasing one would be x1 greater than or equals x2, greater than or equals x3, and so on. If these inequalities are strict, without the possibility of equality, then you'd refer to it as a strictly increasing. But if you just use the term increasing on its own, that kind of allows neighboring elements to sometimes be equal to their previous elements. But never to step down, always be equal or step down, or increasing. Now, as a first task, or a first set of problems that we might look at, we might want to be able to provide a rigorous argument that a certain sequence is increasing or decreasing. And by that, we kind of imagine taking the formula for the sequence, somehow analyzing the formula, being able to give a clear argument or clear presentation, clear explanation of why to ensure that that sequence is either increasing or decreasing. And there are two possible approaches to it. One way is to look at the difference between neighboring terms in the sequence. So that's what this quantity here is, an plus 1 minus an. So that's the difference between one sequence element and the one beside it. Okay? Between an plus 1 and the one that came before it, which is an. If you look at that difference and try and get a nice description of that difference in such a nice way that you're able to compare it to 0. And if you can declare that that difference is always bigger than or equal to 0, or on the other hand, less than or equal to 0, then you'll be able to declare whether the sequence is increasing or decreasing. So if you imagine moving the an to the other side of the inequality, if it was this one on the left, then it would be that an plus 1 is always greater than or equal to an. So that would be an increasing sequence, the inequality on the left. The one on the right, if you move the an to the other side, you've got an plus 1 less than or equal to an. So that would be a decreasing sequence. And similarly, if you can establish strict versions of those inequalities, so without the possibility of equals, just strictly greater than or strictly less than, you'll have established the corresponding strictly increasing or strictly decreasing behavior of the sequence. Or we can look at not the difference between consecutive terms, but the ratio between consecutive terms. An plus 1 divided by an. So that's a term in the sequence divided by the previous one. As long as we're sure that none of our sequence elements are equal to 0, because that would invalidate that. You couldn't look at a fraction of 0 on the bottom. It wouldn't be defined as a number. But as long as that's not the case, you can form this ratio, maybe get a simplified view of it, and then, well, we're not going to be comparing the ratio to 0, because ratios are interesting in their comparison to 1. You compare the ratio to 1, and you either prove it's bigger than or equal to 1 or less than or equal to 1. And that will allow you to say whether the sequence is increasing or decreasing. Because when you move an to the other side, this time by multiplying both sides of the inequality by an, then you'll get increasing or decreasing inequality. Although I think for looking at ratios, yeah, for ratios we might have to insist that the sequence elements are positive, because the ratio can flip sign if one is positive and the other one negative. So I think for ratios we would want the terms to all be positive to make this simple conclusions from these inequalities. Okay, then let's have a look at a little example. There's an example in the notes, and I've got a couple of extra examples here on the slide to look at as well. So our first example is to look at this sequence here, an. An is defined as this ratio here, 5 to the power n divided by n factorial. N factorial, remind you, so n exclamation mark, that's read as n factorial. The factorial of a positive integer n is defined to be the product of n and all the positive integers less than it. So n multiplied by n minus 1, multiplied by n minus 2, etc., all the way down to 3 by 2. So you're multiplying together all the positive integers from 1 up to and including n. That's defined as n factorial. So it's a quantity that increases very fast. And so we may be interested in investigating this sequence and proving its increasing or decreasing behavior. Okay, the details are sketched out in the notes there, but I'm just going to write them out again as we talk through it, you know, before we do the other examples. Yeah. So this is 5 to the power n. Factorial. There we go. Now, you've got a choice between using the common difference or common ratio approach. Okay. We've got a choice between using the common ratio or the common difference approach. And strictly speaking, both approaches are equivalent. If you're able to prove anything with one approach, you'll probably be able to prove it with the other approach. But sometimes one of the two approaches will just work out a little bit easier. It's more appropriate. For this one, for a sequence element defined in terms of exponents and factorials, they're very multiplicative things. And so the multiplicative nature of it should push us towards considering the common ratio. Okay. So we'll examine the ratio of consecutive terms. This ratio of consecutive terms is taking one term, an plus 1, and dividing it by the previous one that came before. You could put an over an plus 1 if you wanted. And key thing is we're going to be comparing this to 1. So an plus 1 is the quantity 5 to the power n plus 1 divided by n plus 1 factorial. Just interpreting the formula in the correct way with placing n plus 1 in the place of n. And then we have to divide it by an. Well, an is just this quantity here, 5n over n factorial. But if we're going to be dividing by it, well, that's the same as multiplying by the reciprocal of the function, of the fraction, So that's our ratio of consecutive terms. It's looking kind of complicated. 4 different factors all multiplied or divided. But you know, you can see that there's cancellation that's going to happen. If you look at the 5s, in the numerator position, we've got a load of 5s multiplied together. In the denominator position, we've got a load of 5s multiplied together. Whenever you've got the top and bottom of a fraction both multiplied by 5, you can just cancel them off because that's just 5 over 5 is equal to 1. You've got a factor of 5 in the top, a factor of 5 in the bottom, you can just cancel it. So all these 5s cancel with all the 5s below, except for the fact that there's one extra 5 in the top. So all of the 5s in the denominator cancel with 5s in the numerator to leave just a factor of 5 in the numerator. So we've got a factor of 5 in the numerator. And the factorials, neighboring factorials or close factorials also cancel a lot. Because in the factorial of n, you've got every positive integer there between n and 1, right together. And in the factorial of n plus 1, you've got every positive integer between n plus 1 and 1, inclusive, multiplied. So in fact, all of these factors represented in n factorial, they're also in the factorial of n plus 1. So all of the factors in this factorial cancel out with corresponding factors in n plus 1 factorial, and the thing that remains is just the first factor, n plus 1, of the bottom factor. Just to make that explicit over here at the side, factorial of n plus 1 is by definition n plus 1 by n minus 1 by n minus 2, all the way down to 3 by 2 by 1. But of course, this bit here is simply n factorial itself. So if you've got n, the factorial of n plus 1 on the denominator, it's cancelled by the factorial of n in the numerator. Almost all of it is cancelled. What's left behind is this one factor of 5n plus 1. Okay, that's certainly a nice simplified view of this ratio, an plus 1 over an. And we're trying to assess which is the bigger part, the numerator or the denominator, so we should compare it to 1. So comparing this to 1, you see, so an plus 1 over an, which is 5 over n plus 1. Well, this is two types of behavior. It's going to be greater than or equal to 1 for every value of n between 1 and 5, or 1 and 4. Okay, so it's 5 divided by a small positive integer for the first few terms. When n gets to the value 4, you've got 5 over 5, which is 1. But thereafter, it's going to be strictly less than 1 for every n bigger than or equal to 5. Once n gets beyond 5, it's always less strict. So that means that we've compared this to 1, so that implies that an plus 1 is going to be greater than or equal to an for every n between 1 and 4, and an plus 1 is strictly less than an for n bigger than or equal to 5. So really, we call this sequence a decreasing sequence. It increases a little, it increases a little bit at the beginning, but thereafter it decreases. So after n equals 5, this is a decreasing sequence. Strictly decreasing sequence after n equals 5. And it's increasing before that. Okay, there's no law or rule that says you have to do an plus 1 over an. You could do an over an plus 1, but you just have to make the careful comparison to 1, and then just, if you did have an on top and an plus 1 on the bottom, our inequalities would be going the other way here. But you'd still get the same conclusion once you cross-multiply the an plus 1. What you do remember is that if you're looking at the ratio of consecutive terms, you do a comparison to 1. If you're looking at the difference between consecutive terms, you do a comparison to 0. Now, I also suggest in the slide there that you can investigate these sequences as well. Now, you can investigate them by working out elements of them on your calculator, but you should also make good use of computers. Now, you're starting to learn about MATLAB, you're starting to get an introduction to MATLAB in your linear algebra and programming skills unit. You mightn't have seen necessarily how to graph a sequence or how to quickly work out values of a sequence in those classes, but I'll just show you here shortly I put this up on Moodle. If you look at this week's section on Moodle, you can see this PDF there, plotting sequences in MATLAB. Just give a little example program that quickly calculates the values of the sequence and plots them out. Yeah, I'll just show this to you now. So as well as having access, everybody's got access. Once you set up your MathWorks account, you'll all have access to an online implementation of MATLAB, which you can access just through a regular web browser. You go to the mathworks.com website. And of course, you can also download your own personal student version of MATLAB and install it on your own laptop or computer as well. So you've got good access to the MATLAB software. And the screen tends to be quite busy here with lots of stuff. You guys, I'm just trying to kind of collapse these things. Yeah, go in. Okay, so the lines in the code that are preceded by percent signs are just comments. They're just there for our benefit. Just it's a text to read. MATLAB ignores them when it's executing the code. And so what we're doing here is we're developing a sequence. It's actually defined by a recurrence relation. So this would be the sequence where S1 is equal to 2. And thereafter, Sn plus 1 is Sn over 1 plus Sn. Okay, so this is the sequence defined by a recurrence relation. And this example shows you how you quickly calculate values of it in MATLAB. And so we're going to store all the entries in an array, which is the word for just a list of integers, or a list of elements in MATLAB. Lists in MATLAB, or vectors, whatever you like to call them, are enclosed in square brackets, and the entries can be separated by spaces or commas. So we initialize the list S, capital S, to hold the first element, which is 2. So that 2 inside the square brackets is this 2 for the value of S1. And then we have what's called a little for loop. You'll be learning about these in the programming skills unit. You've done computer programming before. You've seen for loops, of course. This is one example of a simple for loop in MATLAB. It says for I equals 1 to 100. So it's going to loop through the instructions between for and end 100 times. For every value of this index I, this variable I, starting at 1 and ending at 100. Okay, it's a kind of very simple form of a for loop. And we just got one comment here. So this appends the new element to the end of the array S. So the one instruction to the computer inside the for loop is to take the array S, which it already knows about, and redefine it. Yeah, this maybe slightly confusing, but this line redefines S as its previous value, what it was, and it adds on an extra value. And you see that the extra value it adds on is Si over 1 plus Si. And this is going to take the last element from the list S, which is Si, and it performs the formula in the recurrence relation there, and makes that the new value of S. So that loops through 100 times, it develops S, and puts all these elements in S, and then lastly we plot it. And when you say plot a list of elements and this extra argument here, which is just a decimal point inside single quotes, that produces a graph like this number. I'll just check it now. Okay, so the output that it produces is this graph here. And well, so this is clearly a decreasing sequence. It's plotting 1 point for each element of the sequence. The sequence starts up at 2. You can see it looks like decreasing behavior. So you could take this code and you could change it to more or less give you any kind of sequence. So we could try giving it the sequence we just dealt with. So the sequence we just dealt with, remember the nth element was 5 to the power n over n factorial. So the rule would be 5 to the power I divided by, I think there's a command factorial I. I think that's right. Okay, so you can see the output there agrees with what the conclusions we found on our worked example. The first few elements are increasing, but once you get beyond 5, be about here, the index n gets beyond 5, or in this graph it might be 4 or 6, depending on what's the first thing at position 1. I'm not sure. It might have stepped to the right or to the left, just depending on how the indexing is. It's a bit sloppy. But it increases a bit at the start, and thereafter you can see it looks like it decreases. So that confirms the analysis we did on the page as well. Now, I know you've only just gotten started with MATLAB, so you mightn't necessarily be familiar with a lot of those elements yet, for loops and so on. But you will do as the year progresses. And I put that code, I linked that code there in that link on Moodle. Good. Okay, so let's have a look at a few other examples, just to get used to doing this. So these aren't in the notes, these are some fresh examples. So we'll consider this sequence Sn, which is defined as 3n over 4n plus 1. Well, it doesn't say so explicitly, but let's just assume this is the sequence S1, S2, S3, so the index n is beginning at 1. And the question is to analyze this and figure out whether it's an increasing or decreasing sequence. Okay? So we could feed it into our MATLAB and just get a quick plot of the sequence elements. Of course, that's not strictly speaking a proof. You know, the graph will say that this particular one was decreasing, but strictly speaking, you've only seen that between 0 and 100. So, you know, you can't establish something about the whole infinite extent of the sequence just by computing a few values. You can certainly get good evidence for it, but you know, it wouldn't stand up in court. If you want a conclusion about the whole sequence, you really need a mathematical argument to back that up, rather than just evaluating a certain number of cases at the beginning. So that's what we should do. We should examine Sn. So for this one, we'll examine the difference for variety. So we'll examine the difference between consecutive terms. So we'll look at Sn plus 1 minus Sn. And Sn plus 1 minus Sn is, okay, what's Sn plus 1? Sn plus 1 is this formula for Sn where the index has been replaced by n plus 1. So in the numerator, we have 3n plus 3, because it's 3 multiplied by n plus 1. 3n plus 3. And in the denominator, it's 4 multiplied by n plus 1. That gives you 4n plus 4, then you've got that extra 1. So it gives you 4n plus 5. So that's the quantity Sn plus 1, and then we want to subtract the quantity Sn, which is 3n over 4n plus 1. Now, okay, we've got this. What are we trying to do here? We're examining the difference. Ultimately, we want to compare it to 0. It's not immediately apparent which of those is bigger than the other, necessarily, because both the numerator and the denominator in the first one are bigger than the second fraction, so it's not clear ultimately how different the size of the fraction is. But one way to assess this is to go to the common denominator. So take this difference of 2 fractions and put it over as a single fraction. And so you have to cross multiply the numerators with the opposite denominators to do that. So we've got 3n plus 3 over times 4n plus 1 minus 3n times 4n. Great. You really need to be confident and, you know, happy with manipulating your fractions and adding and subtracting symbolic fractions and so on. And so what does this give us? I won't bother multiplying out the denominator. You don't really need to know what it is. But we do need to know what the numerator is. And so if you look at, if you multiply out all these brackets, let's see what happens. Well, we get a 12n squared when we multiply the 3n by the 4n. But we also get a minus 12n squared here. So there won't actually be any n squareds. And when we multiply this here, we get a negative 15n, minus 15n. But when we multiply here, we get a 12n plus a 3n. So you get a plus 15. So there won't be any n's either. Because the n's generated in the first bit cancel with the n's generated in the second. So the only thing that remains is the 3 by 1. The numerator simplifies a lot. Now I didn't bother multiplying the denominator because I don't really have to. We're going to compare this to 0. By compare, I mean see whether it's bigger than or smaller than 0. Now it's a fraction, it's 3 divided by something. So all we need to know is whether the something that we're dividing 3 by is a positive number or a negative. Because if you divide 3 by a positive number, you get a positive. You get big or small depending on the actual magnitude of the thing you're dividing by. But if you divide 3 by a negative number, you get a negative result. Big or small depending on the magnitude of the thing you're dividing. I don't care about the big or small, I just care about which side of 0 is. So this, well, is this denominator positive or negative? Well, it's certainly positive, isn't it? Because n is a positive quantity. So 4n plus 5 is certainly positive, 4n plus 1 is certainly positive. So I don't really care what it is, precise time. But we do know now that this is strictly bigger than 0. So it's strictly bigger than 0 since 4n plus 5 times 4n plus 1 is surely bigger than 0 and then any bigger than 2. Remember, for these purposes, all we were interested in doing was comparing this to 0. So, just to summarize what we've got there, we've established this, that Sn plus 1 minus Sn is bigger than 0. So, i.e., just put the Sn to the other side, we've got Sn plus 1 is strictly bigger than Sn. So, i.e., a strictly increasing sequence. Agreed? Check our MATLAB, see if that agrees with us. So the ith element is 3 times I divided by 4 times I plus 1. Run that. Okay, so this certainly appears to be increasing. The rate of increase levels off. In fact, the rate of increase is converging to 0, and actually you can see pretty much there that the sequence seems to be converging to 0.75, which is 3/4, of course. You may well be familiar with. May well swap it already. Okay. So is that okay? Any queries about what I demonstrated there? Any questions? Good. Okay, so that's our first close look at sequences. Just to look very briefly ahead, I mean, things will get more involved. We're about to, in the next lecture, we're about to start looking at our definition of convergence. We're going to introduce this very carefully and very formally. And, you know, if you flick a few pages forwards, we're going to get into some very detailed technical arguments, okay? But I just want to go easy on you in the beginning. That's why taking something very approachable and very doable here, looking at increasing and decreasing frequencies. So for your tutorials, you're going to be working on this tutorial sheet for my half of the unit. Okay? So I'll give you all out one of these now. And there's plenty of questions here. By no means will you be giving these full treatment in every tutorial. We've got that 1, 2, 3, 4, 5, 6, 7, 8. So for the tutorial this week, we'll be looking at any of questions 1, 2, and 3.